All right, welcome back. This is our second video on verifying trigonometric identities. And in this video, we're going to prove two identities that are slightly more difficult than the ones we did in the last video, but still not too bad. I think that when you see the homework problems, they're very similar in their form. I don't think you're going to struggle too much with these, especially since you guys are already familiar with basic identities coming into this lesson. All right, let's go ahead and start on the first proof. We want to start with the side of the equation that has a more complicated form. What do I mean? Well, if we look at the left side and we look at the right side, we notice that the left side has two binomials in it and the right side only has a single monomial form, tangent squared x or negative tangent squared x. And it is easier for most students to start with the most complicated side. Less creative, it's a less creative process. As we go forward and we get into harder proofs, you guys are going to have to become more and more creative in your techniques, and to take a simple form and go to a more complicated form is sometimes necessary and requires you to put additional information into the problem that is not already there, and that requires some creativity. All right, let's go ahead and start. Again, starting with the complicated side, we have tangent squared x plus 1 multiplied by quantity cosine squared x minus 1. And if you notice that this is a binomial multiplied by a binomial, you guys learned in Algebra 2 that you can use the trick called foiling when doing this. So if I have a binomial x plus 2 multiplied by binomial x plus 3, I would say, okay, well, if I can take my first term and multiply by both, x times x is what? X squared. X times 3 is 3x. And we have 2 times x, which is 2x. And 2 times 3, which is 6. This will allow us this will allow us to simplify the result very quickly. Much easier than using the distributive property, but we don't need to get into that. Let's go ahead and take our first term, which is tangent squared x, and we're going to multiply by both terms. Notice we have tangent squared x times cosine squared x, which is going to give us tangent squared x cosine squared x. Multiplication just glues things together, guys. And then tangent squared x multiplied by the negative 1. So tangent squared x times negative 1 is negative tangent squared x. And then we have to then take the 1 times the cosine squared x, which is cosine squared x. And then 1 times negative 1, which is negative 1. Notice that we end up with 4 products. 1 product, 2 products, 3 products, and 4 products on the board. Now, this is a strategy, especially as we get into the harder proofs, to make sure that you always look at where you're going. Notice that we're trying to take the left side form and we're trying to manipulate it until we arrive at a form that's exactly the same as the right side. So we're trying to manipulate the left form to get it into the right form. Notice we are trying to get to negative tangent squared x. If you were to look ahead, like if I say equals something, equals something, equals something, we're going to manipulate the form all the way down. Eventually we want to get this to equal, and maybe it takes us another line to do this. Eventually we want to get this to equal negative tangent squared x. If we look at what's already on the board, you can notice that there's already a negative tangent squared x in this problem. And the good news is you guys are not asked to prove things that are false. You are only asked to prove things that are true. So you can assume for your homework problems that if you're asked to prove this to be true, that someone else has already proven it to be true. So the left side is the right side, and you just have to figure out a way to get there. So after foiling this and looking at this form, notice that there is the final form that you want to arrive at. So what must be the case? If you reason through that, you would think, well, that would mean that the tangent squared x times the cosine squared x, and the negative 1 should all go away, and that is exactly the case, and that's what's going to happen. So, as in the last video, I told you guys the biggest identity that you're going to use is that the tangent of x is equal to sine of x over the cosine of x. This is probably going to be the most used identity of all, that you guys are going to use this substitution, because I told you guys that one of the biggest hints is when you see tangents or cotangents in a problem, you want to convert these to sines and cosines when you're just starting out. It makes the problems a little bit easier for most students. So let's go ahead and try that. Now, we're just going to change the tangent squared. We're not going to change the negative tangent squared x to a sine over cosine form. Why? Well, because isn't this supposed to be what we're finally arriving at, it wouldn't make sense to change this. I think you will see why in a moment. So what we're going to do first is we're going to change the tangent squared x to sine squared x over cosine squared x. Notice if tangent x is sine over cosine, then tangent squared is sine squared over cosine squared. I showed you guys this yesterday, that if I have tangent squared x, that just means tangent x times tangent x, which is the same as sine x over cosine x multiplied by sine x over cosine x, which is equal to sine squared x over cosine squared x. So you guys see that if it's squared, it's squared, right? Now, notice it's a tangent squared, which is sine squared over cosine squared, is multiplied by cosine squared of x. And then we have minus tangent squared x plus cosine squared x minus 1. Now, we've changed everything in the problem to sines and cosines except this negative tangent squared, because we expect this to just sit there until we get to the final form, and it will. Notice that if you have sine squared x over cosine squared x times cosine squared x, this is a multiplication problem in itself, and you can think of this as a fraction multiplied by a fraction. I would hope that you guys don't have to put cosine squared x over 1 to see that cosine squared x is a numerator, but if you have to do that to understand, go ahead. Cosine squared cancels with cosine squared, and now we end up with the new form sine squared of x, and I'm going to move this cosine squared x over to the front, plus cosine squared x minus tangent squared x minus 1. And notice that all we did was take the negative tangent squared and the positive cosine squared and flip these around. Why can we do that? Because of commutativity of addition. If I have 3 plus 5, that's the same as 5 plus 3. So I can take these two and I can just move them. And also notice the cosine squared's canceled, leaving us with just the sine squared here. Now, something to recognize. So if I'm supposed to be left, and this is the nice thing about proving things that are already true, you know where you're supposed to arrive at. If it must be the case that I'm left with negative tangent squared when this is all said and done, then shouldn't it be that the sine squared x plus cosine squared x has to cancel with the minus 1? And if this cancels with negative 1, I'm going to underline it. If this is supposed to cancel with negative 1, then isn't sine squared of x plus cosine squared of x supposed to be positive 1? And the answer is yes. You guys have already learned this. You have learned that the Pythagorean identity, I'm just going to put it down here, the first Pythagorean identity says exactly that. And we proved this in class, that the sine squared of x plus the cosine squared of x is equal to 1. And so there you go. There is your substitution. The sine squared of x plus cosine squared of x equals 1. And so what can we now say? Now we can say, I'm going to erase what we're arriving at because we need some more space. We can now say that we can convert this to its other form, which is 1. And now we end up with 1 minus tangent squared of x minus 1. And notice that if you have 1 minus tangent squared of x minus 1, the positive 1 and the negative 1 will cancel each other out, leaving you with negative tangent squared of x, and you have successfully proven the identity on the board. Notice that we started with the left side here, and we changed its form until we eventually arrived at the right side. So if I were to circle this and circle this, there is the connection that we made, that these two things are equal. How did we do that? We did not assume that they were equal to begin with. We took the left form and we used properties of algebra and trigonometry to manipulate the form of it until it eventually arrived at the other form. And so therefore, it must be the case that if the left side is equal to this, which 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 is equal to the right side, then it must be the case that the left side and the right side are equal. Now, let's do our second proof. Notice that this is written, notice that you have a left side and you have a right side, but your right side looks far more complicated than your left side. Again, I told you guys as you start, to start with the more complicated side. It's okay to do this. We can just write the expression, that's on the right side first. So we have 1 over 1 minus the sine of A plus 1 over 1 plus the sine of A. Okay? Now, unlike the previous problem where we had multiplication between our two binomials, in this problem we have addition between our two fractions. And remember, when we add fractions, we have to achieve a common denominator. Now, just because of space, I'm going to move this over just a little bit. 1 over 1 minus the sine of A plus 1 over 1 plus the sine of A. And you guys will get better at this as time goes on, but to keep this video length reasonable, I'm just going to go ahead and move through this question quickly and let you guys ask questions on it. And as I go through more forms, I think this is going to become more clear. All right, we want these denominators to match. Now, they do not match, although they look very similar. 1 minus sine A is different than 1 plus sine A, just like 1 minus 5 is different than 1 plus 5. This is 6 and this is negative 4. They are not the same thing. So make sure that you do understand that these are completely different values. And so to get these to match, we are going to have to literally multiply the left denominator by the right denominator. So what are we going to have here? 1 plus sine of A, and the right denominator is going to have to be multiplied by 1 minus sine of A. And if we do this to the bottom, we have to also do this to the top on both fractions. Okay? Now this is going to give us, notice that we're now going to have to multiply these two fractions together. 1 multiplied by anything is the same thing. So 1 times 1 plus sine of A is going to give us 1 plus the sine of A over, and on the bottom, we have 1 plus sine of A times 1 minus sine of A, and I'm just going to show you. Let's go ahead and take this to the side and FOIL it because we're going to have to do this to save time. 1 plus sine of A and space. 1 plus sine of A times 1 minus sine of A. How do we do this? Well, it was already addressed how to FOIL in the previous problem. We have two binomials. We're going to take the first term and multiply by both. 1 times 1 is 1. 1 times negative sine A is negative sine A. And now we're going to take the second one, multiply by both. Sine A times 1 is positive sine A. And sine A times negative sine A is negative sine squared of A. And the negative sine A and the positive sine A cancel out, leaving us with 1 minus sine squared A. Okay? Now, if you do 1 plus sine A times 1 minus sine A, that is the same thing as doing 1 plus sine A. Oh, well, I guess they're in the same order. I thought they were in reverse order. But anyway, these are going to give us the same denominator. So our denominator for the first one, when I did 1 plus sine A times 1 minus sine A, I got 1 minus sine squared of A. Oops, I wrote X. And, okay, so this is the product of the first two fractions, and then the product of the second two fractions. Let's go ahead and put our addition sign. We multiply the top first. 1 times 1 minus sine A will give us 1 minus sine of A over, and here if we FOIL this, we would get the exact same thing, 1 minus sine squared of A. Now remember that when adding fractions, once you have that common denominator, again, like I said in the last video, if you do 1/2 plus 1/3, you would multiply the denominator of 2 by 3, you would multiply the denominator of 3 by 2, and if you do this to the bottom, you have to do it to the top because you're multiplying by 1. You would have to do the same thing to the top and bottom over here because you're multiplying by 1. Because 3 over 3 is 1, 2 over 2 is 1, you're not changing the value of the problem. This gives you 3 over 6 plus 2 over 6 because you just multiply, and then when you add these, the denominator of 6 stays the same, and you add the top, it gives you a 5. So remember, when adding fractions, the matching denominator is then going to remain the same, and you're just adding the top terms, and you're taking two fractions and combining them into a single fraction. So these two fractions will now combine to a single fraction form with a common denominator of 1 minus sine squared of A. So notice, keep writing X. So notice that the denominator remained the same. And now we're going to add the top. So when you add the top, you're literally doing 1 plus 1, which gives you 2. And you're doing sine A plus negative sine A. Remember numbers. 5 plus negative 5 would give you 0 or cancel each other out. Same thing with sine A plus negative sine A. These would cancel each other out, giving you plus 0, and 2 plus 0 is just 2, so they go away. So we end up with 2 over 1 minus sine squared A. All right, at this point, it will help you, again, to look at where you're trying to go. Notice that you're trying to get to a form of 2 secant squared of A. So eventually, this is supposed to turn into a 2 secant squared of A. So what's going to happen is equals, equals, equals until eventually we arrive at 2 secant squared a. This is where, thinking of this as a road map comes in handy, where I know most of you guys use GPSs, but back in the day when we read a map, you would look at the city that you're driving from. So say you're going from Danville to Greensboro, you would first start by looking on the map at Danville and working your way out until you found Highway 29, okay? And Highway 29 is the road that goes all the way down to Greensboro, but you're not going to just Greensboro, you're going to a specific location in Greensboro, somewhere in the inner city. You would have to then look at Greensboro, which is your final destination, and work backwards on the map until you figured out how those inner city roads would connect back to Highway 29 so that you could get the whole route to connect. What do I mean? After you start working your way from, we'll call this Danville, on the map, and you figure out, okay, I've got to get all the way down here to Highway 29, well, you have to go to a specific location in Greensboro. So you have to work this back. This helps in many of these problems. You have to work this back until you figure out how this will connect with Highway 29, okay? This being Highway 29 in the middle. So what are we going to do? Well, we're going to convert this backwards by turning it in again. Like I said in the last video, it always helps to turn things into sine and cosine forms. Notice that we had a sine form in the original problem, so I didn't mention this. But in this, you don't. You have 2 secant squared a, and if you remember that the secant of a is equal to 1 over the cosine of a, then you can say that the secant squared of a, this is going to equal 2 times 1 over the cosine squared of a. And if you work that backwards, I'm going to work it back to this step, that 2 will multiply by the top of the fraction. You end up with 2 over the cosine squared of a. And now if you look at this form and this form, you see, okay, we see that we have a denominator of 2 on both of these. And again, I know, assuming we didn't make a mathematical error, I know that these two have to be the same, because what I am proving is true already, that it must be the case that this 1 minus sine squared is the same thing as the cosine squared. And if you think about, again, what have we already learned? It was used in the last problem. Here's the hint. Anytime you see sine squared, or anytime you see cosine squared in a problem, you need to be thinking about that Pythagorean identity that we learned. Okay, I just wrote it earlier, but I'm going to write it again. You guys are supposed to have committed this to memory. That the sine squared of x, I'm going to use a since we're using a in this problem. Sine squared of a plus the cosine squared of a is equal to 1. Or you could use theta instead of a, or you could use x instead of a. And notice that we can manipulate this equation. In the last equation, we took the sine squared plus cosine squared out and replaced it with the 1. But in this equation, we have a 1 minus sine squared, and we're trying to convince our audience that 1 minus sine squared is the same as cosine squared. And if you look at this, yes, you can manipulate this true statement by taking the sine squared of a and moving it to the other side, giving you cosine squared of a is equal to 1 minus the sine squared of a. And there it is, okay? So notice, if the sine squared of a plus the cosine squared of a is 1, then it must be the case that the cosine squared of a is equal to 1 minus the sine squared of a. And so what have we shown up here? By manipulating the Pythagorean identity, we do this over to the side. You have now convinced your audience that cosine squared is equal to 1 minus sine squared. You guys are going to become so strong with this manipulation. Notice that if I have sine squared of a plus cosine squared of a is equal to 1, you can also manipulate it this other way by moving the cosine squared to the other side of the equality, giving you that the sine squared of a is equal to 1 minus the cosine squared of a. You guys are going to get so good with this that every time you see on these proofs 1 minus sine squared, you're going to just note that you can replace that with cosine squared. And every time you see 1 minus cosine squared, you guys are going to know that you can replace that with sine squared. Well, guess what? You're done. So if you put an equal sign here, notice, because of your knowledge of the Pythagorean identity, we know that 1 minus sine squared of A is equal to cosine squared of A. The proof is finished. And again, we started with the left side of this thing, which was this. We manipulated its form. We manipulated it once, twice, 3 times, 4 times, until we finally arrived at the final step. And notice that we have shown that the left side, which is this, is equal to the right side, or actually I guess I'm backwards here. The right side of this is equal to the left side. You can turn these things around because of the symmetric property of equality, and therefore we have proven the statement on the board. Guys, have a wonderful day, and I will see you in the next video.